I'm going to talk today about part of the efforts that we do in my group about using machine learning for closure models, for computational fluid dynamics, in particular for large-scale simulation. So first, I want to acknowledge the people from the group that they work on this. This is a big project. There are many people involved. I want to mention first Yuan Ling, that he is taking the lead of many of the results that I'm going to be showing today. And the model I'll show today has two components. One is like lowest speed, another is highest speed. So highest speed, I have Roma and Yuan, and that's supported by NASA. So I also want to mention our collaborator there, Clark. And then there is a low speed component, and that's supported by Boeing. And there is Gonzalo and Imran, and then our collaborator from Boeing, Conrad, and Morimani. And we also have some support from NSF. And part of this, the prototype of this model was developed in a summer program in Stanford. So I also wanted to acknowledge that and acknowledge some people that help us to generate the database. So this is Perviz, Moin, Raul, Michael, and Ahmed. So to give you an overview of what is the goal of what we are trying to do here, and then I'll explain a bit more the technical details. So what we call this model is the building block flow model project. So it's a closure model for large-scale simulation. And the idea is that we want to develop this model that it will give you good predictions across many different flow regimes. So here in this slide, I'm showing different simulations that we have run in my group. And you can see there are different flow speeds if you want. So one is like a compressor and a turbofan, could be a saxonic or transonic flow. We could have another saxonic flow, but on an aircraft, or then going faster, the supersonic flow, and even faster, like hypersonic flows. But the key idea is that instead of having 20 different models, and each of them is specialized in one particular flow and is good at only that flow, we would like to have only one model that is very good at all the flows. Now, whether that's possible or not, it kind of remains to be seen, but at least from the work that we have been doing, we can show that you could actually have one single model that will do a very good job across many different flows. And what I have at the bottom is kind of the conditions that we impose ourselves for the model. So what we want this model to be could be applicable to arbitrary geometries. As you see here, the model will account for some physics, but it should be able to scale up to new physics. It has to account for the numerical schemes and provide some explainability about what the solution is, and also will have some confidence in the prediction and computational cost. So it should be competitive. Okay. So there is no paper manuscript for this model itself. So we have been developing this model in small pieces that we then combine together. But if you're interested, I'm showing here some of the papers that they contain, many of the components I'm going to be talking about here today. If you go to my website and you look for any work that is called building block flow model, somehow then is related to this model. And what I'm showing here today is kind of the overview of all this. So this is the kind of the outline of what I'm going to do today. I'll talk about the problem formulation. For those of you that are not familiar with large-scale simulation, I'm going to talk about what this is a grid scale model and one model. And most of the talk is, or maybe half, is the point number 2, that is explaining how we build the model. And the last part is validation. So we test the model in cases that are very different from the training set, just to make sure that it will work okay in those scenarios. Okay. So let me start with the beginning of this. So this is the framework that we work on. So this is a framework of computational fluid dynamics. Essentially, what we have is, I'm using the aircraft as a representative, but obviously the model could be applied to any other case. So we have this grid that is in blue. If we were able to zoom in close to the airplane, let's say close to the wing, we will see this surface. And then we will have this blue grid that is a grid that it is what we can afford is usually very coarse. It is not able to resolve all the small scales. So all the scales would be represented by these eddies that you see in the background. So some of them are captured by the grid, others are very tiny and you cannot. So because we cannot capture those tiny eddies, then we need to account for them because they still have an impact on the forces of the aircraft or the heat flux or whatever we want to compute. And conceptually, in one model large-scale simulation, we divide that into two problems. One is the grid scale model. So this is accounting for those small scales that we don't resolve and they are off the wall. And then we have the wall model. So the wall model is accounting for the effect of the small eddies that we cannot capture are exactly at the wall. So typically the grid scale model will gather some information, local information of the flow and account for that and make the prediction of, if I bring now the equations here, typically I'm writing here the conservation of energy, mass and momentum and boundary conditions. So the grid scale model is accounting for, it shows up in the equations on the right-hand side, is correcting the right-hand side to account for the small eddies that we miss. And then the wall model shows up in the boundary conditions. So we have a wall model for the heat flux and we have a wall model for the wall shear stress. And the wall model will gather some local information of the flow, density, velocities, temperature, and make a prediction of the fluxes at the wall. And those are imposed as a boundary condition. So essentially what we do is we resolve the LES equations that are here. And then these boxes in red, we need to have a model for them. So what we are doing here is designing these 4 models that I'm showing here. And these models are redesigned from scratch, so they don't take any legacy from any previous models, so all of them are done brand new. Okay, so this is the paradigm that we work with. There are other approaches to CFD that are not wall model LES. Others are related to runs or unsteady runs, the ideas. There are many, and probably many of the ideas that I mentioned here, they could be applied to those cases. It just happened to be that I was more familiar, or my expertise was more wall model LES, and that's why I took this direction. So let's now jump into the model itself and what the model does. How is the model built? But let's discuss what is the main idea of the model. That is also the main assumption, the strongest assumption of this model. So let's consider this aircraft. So the aircraft, I want to have a simulation of the aircraft, and this is absolutely unaffordable. So I would need 10 to the 25 degrees of freedom, or maybe even more. So there is no way I can fit that in any supercomputer. So I have to give up degrees of freedom, and I need to use a grid that is very coarse. And then I am suddenly in this paradigm of wall model LES. So the idea is that if I were to look at a small region here, the effect of the missing scales in this complex case locally can be retrieved from the smaller scales of simpler flows. So on the right, I have these simple flows. So these are affordable simulations, and this is where it's going to be my training set. So these simulations, I can resolve all the scales in space and time. And I know everything. I can extract how all the scales interact. So I have all that knowledge. So in a way, I'm mapping, this is not a scale, but you can think I'm mapping this red rectangle here that I have. I'm missing some scales there. So what I'm doing is to looking for the effect of those scales in my training set. So a combination of them, usually a nonlinear combination. So this training data is not resolving in a way. I don't care so much about the larger scales of this training data, because the larger scales are definitely unrelated to an aircraft. But I'm looking for more intermediate scales. So missing the small ones and see how that is affecting the intermediate scales in these cases. Here I'm showing 4, but obviously we'll have many more cases. So this is the main assumption. And this is what we call the building block flow assumption. And obviously this has to be satisfied up to a degree of freedom, otherwise that will propagate into errors, into the predictions. There are other basic requirements that I don't go into those much, but these are mandatory for any model. They have to be invariant under rotations, translations, they have to be Galilean invariant, and they have to be dimensionally consistent. Otherwise the model will break. And other assumptions beyond this main idea here is the model is assuming some spatial locality of the effect, so that it doesn't have these history effects. It's assuming that the effect of any history effect, it has to be captured by the grid of LES. And only the small scales, those are local. Quasi-equilibrium, again, like unsteady effects, the small scales are in equilibrium. It's also assuming some similarity between outer layer and inner layer, because the inner layer here, very close to the wall, is completely gone. So I'm assuming that these larger scales are not affected by that. Other assumptions are eddy viscosity assumption that I will discuss for the grid scale model. There are many more, but probably these are the most important ones. So the way we are going to do this mapping, so essentially I'm going to have a function that is parameterized with a neural network, and that's what is going to allow me to recover the effect of the smaller scales on the large ones. So the model had these three components, or the way I'm going to explain it in three components. What is the database that I use for training the model? How is the model designed, the architecture? And also the model contains an explainability. By this, what I mean is like, the model will also give me some information about why it's doing predictions. So what are those predictions coming from? So let's start with the training database. So the training database are very simple cases, these direct numerical simulations, and they are turbulent post-Couette flows. That means that we have two walls. One is moving with a velocity relative to the other, and there is also a pressure gradient. So that's what is represented here. And by changing the Reynolds number based on the walls and Reynolds number based on the pressure, I can generate different mean velocity profiles. And these mean velocity profiles, in a way, they are mimicking the effect of pressure gradients. From zero pressure gradients, adverse, favorable, even separation in a way, because you can have flow reversal, and that will be what you see here in this mean profile. And these cases, some of them, they have a smooth wall, and some cases they have a rough wall, because the model also accounts for some under-resolved roughness. And these rough walls, they have different topologies for the rough wall. And on top of this, we have different Mach numbers. So the model will solve cases that are incompressible and cases that are compressible up to Mach 3 or Mach 4 in that range. So we do a parametric sweep, and this we have been generating this database for a while. So in total, we have 700 DNS cases. And I have a summary here of the typical, based on the Reynolds bulk, Reynolds number, the Mach numbers, and a smooth wall, and we have 50 different roughness surfaces. So in a way, what are the physics model? So these are the physics that we are trying to capture: zero, adverse, and favorable pressure gradient, separated flow. The model also captures laminar flow. It's not shown here, but that's trained with analytical solutions, compressibility fact, and with that, we capture heat transfer and the roughness surface. And this is now we are updating some of these database to include new building blocks, but in a way, for this presentation, this is the version of the model that we have been validating the most. So I'm going to be talking mostly about this version for now. So this is the training data, and the training data comes from DNS, but we don't use the DNS itself. And the reason for that is because these LES cases that we run, typically the grid is very coarse. And when the grid is very coarse, the effect of the numerical scheme in your solver is very important. It's almost order one. So it really matters what you are, the numerical schemes that you are using. And the model has to learn what is the numerical scheme, and it has to correct for that. So a typical approach that many people follow before is they use filter DNS. And that is, it doesn't account for this effect of the numerical scheme. So we don't do that, and we don't do directly the DNS data. We don't use it directly. What we do is we collect mean quantities that we care about. We care about mean velocity profiles, mean temperature profiles, the fluxes at the wall. And with that, what we do is we run a wall model LES of the same training data. So I set up exactly the same training data I have DNS for. I run the case, and then I solve an optimization problem. I adjust my grid scale model. In this case, I'm showing here the eddy viscosity. I adjust the eddy viscosity and the fluxes at the wall such that I match the DNS. And essentially, this is not a model in the sense that I know the solution and I'm imposing that. But this is the data that then later I'm going to use to train the model, because now this data is aware of the numerical schemes that I have. So in a way, these are the three steps we follow. We extract the mean quantities we care about, and those are the ones that the model is going to be trained for to predict. We run all the database, the 700 cases with those, using this optimization problem, and it will match the statistics. And that world model LES data that is coming from the same solver that we are going to use now to implement the model, now that's the training data that we use to generate the model, and it's taking into account the numerical scheme. So with that, then we have our data ready, and now what we need to do with the data is to train the model. So to train the model, I'm going to go back to, again, this schematic of an aircraft, and I'm going to zoom in this red rectangle. So I'm showing here how the grid might look like. This grid in particular is following a Voronoi pattern. And if you remember, so the model is applicable to any unstructured grid. So in principle, it should be applicable to any type of grid topology. So the model has 3 neural networks, the way it's parameterized. One is taking care of these control volumes that are far from the wall, in a way. So it will take as an input invariance of the velocity gradient tensor and some information about the grid size, viscosity, densities, and it will pass through this feed-forward neural network. That is very basic one. And then it will give you the effect of unresolved scales. And that's done through the viscosity. The next neural network is the one that is for control volumes that are touching the wall. Those are a bit special because in this case, I need to account for 2 things. I need to account for the fluxes at the wall and also for the under-resolved scales. So that's why I have a second neural network. It takes almost the same information, but it also takes some local velocity here, temperature, and again, it predicts the viscosities there. And then I have the third network that is the fluxes at the wall, and that will take information about the same information that is happening locally in that control volume, and it will predict the tau wall, and Q wall is the heat flux at the wall. The other component that I mentioned is that maybe there is some roughness that we cannot resolve. That means that there is some roughness happening across this control volume. We would need a lot of grid points to resolve that roughness, so we give up and it's under resolved. So that information also goes into the model. That's what I'm showing here in this schematic. Imagine that there is some roughness here in this control volume, and it looks like this. So part of the roughness might be resolved by the grid, but the one that I care about here is the one that is under resolved. So it's a grid scale roughness. So from that, what I need to give the model is some roughness parameters, is some like average geometric parameters, like the typical height of the roughness, the first moment, the slope. So all that will go into the model, and then the model will account for that in terms of the wall stress and heat flux. It will account for the fact that we don't know that the roughness is under resolved. Usually they tend to increase the heat flux and the wall shear stress. So this is essentially the picture of how the model works. So I have these 3 neural networks. And so in a way, from the point of view of the predictions, the model contains these 3 networks. And they are always the same 3 networks everywhere. So now there is another important point that I like to discuss here, because it helps us a lot to construct at least some components of the model, is that just because of dimensional consistency, we need to impose that the inputs and the outputs of the model, they have to be dimensionless. At least you should be able to write them in dimensionless form. And that you just apply Buckingham Pi. But there are infinite number of ways of generating these dimensionless numbers. What we do is to find what are the dimensionless numbers that they help us the most to make predictions. And the way we do that is what I'm trying to explain here in a very summarized way, but it's based on how much information the input has about the output. So essentially, if you think of this model, I'm calling pi are the dimensionless quantities. I have pi naught is what I want to predict, for example, the wall shear stress. I have a model that is my neural network, and my model will depend on m dimensionless inputs, pi 1 to pi n. So I can schematically write this, show that like this. So the blue would be the information that my input has, and the yellow or orange here is the information that my output has. So how much I can predict from the output is related to this overlap. And all these quantities come from information theory. One is the Shannon entropy, and the other one is the mutant information. So it's not very important, maybe, this formula, just beyond the fact that you could compute this beforehand. And what we are trying to do is to solve an optimization problem. We are trying to find what is this overlap here and try to maximize it. And in a work that I did with other of my students, you can show like this is not only a heuristics, like it's not an intuition, it's actually a theorem. Like you can show that this relationship, this inequality that you see here, and this inequality is that the minimum error in any norm P that you can find between what you want to predict and what your model can predict is bounded. It's a lower bound, and the lower bound depends on many quantities, but in particular, it depends on this overlap. So the higher this overlap, the smaller the error that you can get to make predictions. So that's essentially how we take all these ingredients and we pose this optimization problem. We want to find the dimensionless inputs that will give us a dimensionless output, such that this quantity here on the right-hand side that we call epsilon lower bound is a lower bound error, to minimize that. And what is nice of this is that this can be done before we find this model F. So this is before training the neural network. We can find what is the best input and the best output for that neural network. So we do this, we find those dimensionless inputs and outputs, and then we train the network. So that would be what we do. We take all the training data and we apply this to our training data. I hope that this overview is more or less clear, but if you are interested in more details about this approach, then we have a paper that is called Dimensionless Learning, and you can also find it in our website. So the last part is the explainability. And just for the sake of time, I'll describe a few components of this. I'll show later a few examples. Maybe I'm not going to go in such a small detail here. But the model has two components that are related to explainability, and they help us to understand what the model is doing. So let me discuss the first one. So the first one is a confidence score. So what we are trying to answer here is this question: is how similar is the input to the training data? So I have these building blocks. I train my modeling on those building blocks. And now I deploy the model in another case that has nothing to do with those cases, that full aircraft. So now the model, what it's trying to say is like, did I see this before? That's the question it's trying to answer. So maybe every time that the model gets an input, it will ask this question. And the answer might be yes. It means like, well, this is very familiar. Like I know what the predictions for this input should be. And that will give us a high confidence. But could be the opposite. Could be that sometimes the model will get an input and the input is very far from your training data. So the model obviously will give still a prediction, but that prediction will come with a low confidence. And this is what I'm showing here in this example. This is the world model applied to the aircraft over the surface. And it's ranking at every point, I have a confidence. Sometimes the confidence is 100%, but sometimes the confidence drops to very low, even 0%. So it means that if you want to, the model is working in extrapolation mode. So we use this then later to try to inform the model to improve it. The way this is implemented is using attentive neural process. But to be honest, it's very simple. It's just measuring the distance between the training data and the actual input that you get. This is just a way of doing it in a very smart way. So this other part related to explainability is the classifier. So the model will give us predictions, but it could also answer this question: is what part of the training data is used to make that prediction? So I told you that the training data contains these building blocks that they are trying to mimic adverse pressure gradient, separation, attach flow. Could be different type of roughnesses, could be low Mach, high Mach. So at every point, the model will also tell us, okay, this is what I think is happening. I think that this flow, I'm using 10% of this type of flow, or another 50% of this other type of flow. Could be 10% adverse pressure gradient, 50% low Mach, 20% smooth wall. So it will get all these classifications that then you can look at. And the idea of this is to make sure that the model is making good predictions for the right reasons. and we don't have the right prediction for the wrong reason. That could happen. Actually, that happens a lot. So for example, if I know that the flow is attached because I know the answer or I have experiments in a particular case, but the model is telling me that is using the information of the training data from separated flows, then obviously that is a problem, because I don't care anymore if the prediction is right or wrong, because obviously the model doesn't understand what is going on there. So we also use this to, every time we revise the model, learn what the model is failing and try to understand what is the problem, and also to try to know in which direction we need to expand the training data. In a way, both of these we use for that. And for these two cases, this classification and confidence score, I'll show some examples later. So that's essentially the overview of the model. And this is showing just how we develop the model. So in a way, this is not a frozen model. It's a model that we keep developing different versions. So we have a training data, we implement the model, we test it in simple cases, more like a verification in the same training data we train for. It has to do a good job at least there. Then we have other complex cases. They are not in the training data. We validate there. We look at the confidence. We look at the classification. We look at where the model is underperforming. And we use that to tweak the model. Typically, the conclusion is generally that we need a better training data, or different, like we didn't capture the physics. And we iterate again. And every time we go around, we generate a version. And the model itself is implemented in GPU. The solver that we use is Charles. And this version that I'm presenting here is the version 1.5 of the model. And we are now trying to, we are now developing the version 2, but it will take maybe 1 year until the version 2 is finalized. But many of the things that I'm showing here are obsolete in a way because we are improving them. Okay, last thing before I show you some validation cases are related to the computational cost. That it tends to be also something that you have to pay a lot of attention, because if you are not careful, then it's true that the model might do a good job, but it will be extremely expensive. So we put a lot of time in optimizing the model for GPUs. So this is a test case. We ran this aircraft. This is it's called the CRM high lift. I'll mention that a bit more. And what I'm showing here is 2 other models. So the Bremen model with equilibrium wall model, that's what it means, is EQWM. And the red one is the DSM, is dynamic Smavorinsky model with equilibrium wall model. And in green is our current version. And this is a normalized time of the full solver. So how much time it takes the full solver to give, I think it was 10,000 steps. And then we take that time for the 3 cases, and then we normalize with the Bremen, because the Bremen is the computationally fastest. So the Bremen is 1. And well, you can show where we are in a way. So the most expensive one will be DSM, that maybe is a 10% overhead. In our case, we are between almost no overhead and then 10%, 15% overhead. So the main takeaway here, or what I wanted to show, is that the model, computationally speaking, is similar to what you would use. So if you do a simulation of an aircraft, this is using exactly the same grid, exactly the same solver, but all of them for GPU. You see that the times will be very similar. So I'm not going to show times later when I show the validation cases. I'm going to be comparing with these 2, but I'm not going to show any times. The idea is that comparable. So the cost is not very large. And this, again, we put some time because at the first versions of the model, this version, or the version 1, tend to feel like maybe 10 times more expensive or 5 times. So that was obviously not acceptable. But now I think that we managed to make it very competitive. Okay, so that's essentially everything I get from the model overview. If you want to know more technical details, yes, please go to the papers, or just reach out to me and I will point you exactly. I will let you know, or I just point you exactly to what paper you have to look at. So now, validation cases. I'm showing here like an overview of pictures of validation cases. So we are really trying hard to build like a benchmark collection of cases that is very wide as possible. And we have a variety of things. So some of them are very simple, like the 2 channel flows or just a pipe. Then we increase complexity. These are bumps or aircraft-like. We also have cases with high-speed flows like a compression ramp or hypersonic, turbine blades. We have also airfoils. Uh, in total, we have many of them. We have maybe 300 untrained validation cases. But I also want to mention that it looks like 300 is a good number, but most of these are simple. Most of them are essentially very similar to the turbulent channel flow, boundary layers, things like that. And we are really trying to put together more cases that are complex. And if you have suggestions, please let me know, because this is probably one of the challenges of how to find good cases that we have actually the information that we need to validate against. So I'll pick a few of these here and show you the performance of the model. Let's start with this simple case. And it's a turbulent pipe. I picked this mostly because this is a Reynolds tau, almost 40,000, that obviously we didn't train for this. But the idea is like, if all the inputs are currently non-dimensionalized, and the scaling, the model was able to pick up the scaling of the problem, then it would be able to extrapolate in this. I mean, in the sense, it's not extrapolating. It's really, I non-dimensionalize things such that this will fall in my training data. So a visualization of the pipe with the grid. Typically, we aim for very coarse simulations because that's actually the number of points that you will allow. In a real case, maybe you have 10, 20, 50 points per boundary layer thickness, maybe 100 if depending on the problem. And what I show here is the mean velocity profile. And in all the cases that I'm going to be showing next, I try to follow the same colors and symbols to compare with. We are comparing with Breman and equilibrium world model, orange triangle, dynamic Smagorinsky with equilibrium world model, this red square, and typically Lash is experiments. So this is the mean velocity profile, just to show that we do a better job. And probably more interesting is the wall shear stress that you can see here, but I'm showing here the prediction. So in our case, we get 3% error. The Breman will get like 13, and the DSM will get a 22% error. So at least in this simple case, that again is not in the training set, and high Reynolds number, we are able to do a good job. Next one is more interesting. So this is a case that is very challenging and people from the CFD community really like a lot. It's a bump that has a Gaussian shape. And the interesting part of this problem is that you have separation. It's a smooth body separation. It's difficult to capture. So this is a high Reynolds number, but low Mach. I'm showing here how the grid looks. So nothing very fancy. There's a few layers stacked on top of each other of refinement, a visualization of the flow where you can see the separation region. In this case, the flow goes from left to right. And again, as before, I'm showing the BFM version 1.5 compared to the Breman and dynamic Smagorinsky, both with equilibrium world model. What we have in this case is pressure coefficient and the friction coefficient. So these are quantities at the wall. So for this grid resolution that still is coarse, you see that we are able to do a much better job. The symbols are the experiments for the friction coefficient and for the pressure. And maybe the only part that is off for all the models maybe is the upstream friction coefficient. I think that this is very sensitive to how we tune the inflow to the simulation. And in a way, this is scattered there. We don't match that exactly. But I would say that once that's forgotten and we just get into the bump, then predictions look good. I also want to highlight here that this is, if we refine the grid much more, then dynamic Smagorinsky actually would do a good job too. And the Breman still will not be so good, but refining the grid obviously will help the other models. And I'm also showing here mean velocity profiles. So this is I'm showing schematically the bump, different locations. You could see why the predictions were good. Essentially, we follow the experiments well, and we are able to capture that separation. Maybe at the very end, the mean profile is slightly off, but again, the other cases for this grid, they were almost completely missing the separation. And you can see that the orange and green, they are almost together. The prediction is almost the same, but it's off. Okay. So now this case, that is an interesting case because it's a real application, is the CRM stands for Common Research Model, and IHL is the high lift. So I'm following exactly the same nomenclature. This is a case that is a low Mach still, high Reynolds number. I'm showing an insight of how the grid will look like. And the grid is the same for all the cases. In this case, we just follow some best practice that the people from Boeing told us to follow. I show here lift coefficient, the polar, the lift versus drag, and the moments, and this is for different angles of attack of the aircraft. So overall, you see that at least this is what we want to see, that even if we don't predict things with a high accuracy, still we always push the solution in the right direction. And this is what you could see here. If you look at the lift, for low angle of attack, maybe we are comparable. At high angle of attack, we tend to do slightly better. In the case of the polar, we do actually much better. And the moment is one statistic that is really showing problems with the model. So here, the angle of attack is in the vertical axis, but you see the moment, this is the pitching moment, so how the nose tends to go down. For high angle of attack, actually, it's true that we push the solution in the right direction, but all the models, to be honest, are quite off. And I'm going to use this particular case also to motivate the use of the confidence. So this pitching moment is known to be very sensitive to how the forces are distributed. So that's why the lift and the drag could actually be okay, like a good prediction, because it's integrated force in a way that doesn't depend how that force is distributed so much. But the pitching moment will depend a lot of how over the wind the forces develop. So this is essentially on the left the prediction, and on the right the confidence. So this could help us in a way to identify what the problems are. And in this, over the wind itself and the nacelle, things are okay, but you see that there are some black regions. Those are the low confidence region. You have some stripes that are at the leading edge of the nacelle and the wind. This is the slat that is deployed in this case. Those, we understand what happened is that the bonded layers are so thin that we have 0 points per bonded layer. So 0 points per bonded layer, the model will, yes, give you 0 confidence. So because you are not resolving anything. But then the other part is this corner here at the fuselage and the wingtip. And we know from the experiments that there may be separation there. And our guess here was that the separation that our model learns about from the training data, it doesn't follow the same physics as the separation that we have here. So that's essentially what our conclusion from this is that the model wasn't able to capture this physics, and because of this wingtip and the roots, those forces are not the correct ones, that's affecting the pitching moment. Another way we use this confidence is for the refinement. So once that we see this, we can also try to refine in these regions and see if that will push the confidence up. Like we did in this case, it will definitely push the confidence up a bit, but still it will remain quite low. So we actually need to improve the physics. This is kind of a conclusion of the model. Another aircraft-like flow is called junction flow. Looks similar, it's kind of simpler, but in this case, the experiment has mean velocity profiles that we didn't have before, so it complements the other experiment in a way. So I'm showing in this case, I'm comparing only with Bremen, because if I put the DSM, there are too many things going on, but it's kind of comparable to the Bremen. So I'm showing mean velocity profiles in these different locations, A, B, and C. I'm showing 2 components of the velocity profile. And again, the dots are the dash lines are the experiments, and the blue BFM and triangle Bremen. So you see that when the flow is attached here, we do very well. Even here, close to the fuselage and the wing, here is also doing a okay job. Then in the C is where we have some separation, is the trailiness separation. So that, well, again, what we see is something that we like. We push the solution in the right direction. That's why the circles get closer to the dash. But we are not predicting well that separation. One reason is also, again, that we have very few points. We are testing the model in the extreme conditions where the grid are very coarse. If we keep refining, we get much better. Also, the other models get better. But the idea is that we tend to get better, or we tend to get always closer to the true solution. So we are always pushing the solution in the right direction. But I also picked this grid because I can show you the part of the classification of the model. I'm showing some of the classifications that are meaningful. So the model could tell me if I am in a free stream laminar flow, favorable, 0, or adverse pressure gradient of separation, and in different locations. So you can see the percentage that the model is assigning to different locations, and also the confidence. So in A and B, kind of relatively high confidence, and mostly is detecting something that makes sense with the physics, either some favorable or zero pressure gradient here. In B, we know the flow is decelerating, so a lot of adverse pressure gradient, maybe separation sometimes, or maybe a mix between zero pressure gradient. And in the location C, actually the model knows somehow that there is separation there, but the confidence is low, it's 20%. That in a way is good because we know the prediction wasn't right there. And in this case, we know the solution, but in other cases, we don't know the solution. So I think that this is helpful to know when the model might be failing. So again, this is an example of how we can use the confidence to now reevaluate the model and say, okay, the model is not able to capture physics there, or either the grid was very coarse there. This fits within the explainability, like try to understand what the model is doing. Okay, so now I'll have a couple of cases more. This is now the high-speed cases. This is really challenging because there isn't so much information about high-speed cases, and experiments are high quality, and they measure many quantities that we can validate against. But this is a nice one. This is from Prince. It's a compression ramp that is turbulent, and also it has roughness. So all the plate is rough, and then you have a shock wave, you have a separation, recirculation, you have reattachment. So many things going on. And the Mach is a high Mach, is a 8.3. But this is low enthalpy, meaning that there is no chemical reaction here. And the model does not account for any chemistry. So it wouldn't be, we shouldn't apply it. I mean, we could apply to chemically reacting flows, but obviously predictions are not going to be good. So this is the heat flux experiment, and this is the blue line is our prediction. So maybe we get of the order of 10% errors, depending how you measure them, but we could more or less capture the trend. And what here, I'm not comparing with any other models. And the reason for that is that there is no equivalent model that I could apply here. So there is no wall model LES with a wall model that will be able to predict the heat flux for a rough wall at high speed flows. I could compare with a equilibrium wall model. It's very horrible, and I used to do that, but then people complain a lot because it's true that maybe I shouldn't use it here. So I just don't anymore. So, but you can see that, well, predictions of the order of 10% error, then you need to decide if those are reasonable. And the last case is a bit more complicated, is this hemisphere. So this is a hypersonic flow, Mach 6, high Reynolds number, still cold. Everything is very, temperature is very cold before the bow shock. And it has also roughness. So you see this is it has this sun grain roughness here. And what the quantity, usually when we go to high speed flows, the quantity we care about is typically the heat flux. And actually that can be measured. I would also like to compare the skin friction, but typically that's very challenging in experiments. But the heat flux is usually what we care about. So we usually here is a representation of the temperature. So that just to show it remains low all the time, even after the bow shock, it will go up. Then you have the wake. This is the heat flux. And I'm normalizing with respect to some reference from the heat coefficient such that the stagnation point is 1. So that's how the heat flux is normalized. And the X is just moving along downstream. So here I'm showing our model, 1.5. These are experiments from NASA, from Hollis, that collected this, and those are the dots. And in this case, I also compared with no model, just to show, I could also do that maybe in the previous case, just to show that if you have no model means I switch off the wall model. So then you see that prediction is pretty different. So essentially there is no, the heat flux is not enhanced by the compressibility effects and the roughness. So you see that in this particular case, a factor of 3 that you can get in the heat flux. Okay. So those are all the cases I wanted to show you. We have some more in the papers, but at least it gives an overview of what the model can do. But I would like to mention a few limitations of the model. So the first one is, I don't know if it's a limitation, but it's kind of obvious thing that the model is, the strongest assumption is that in the training data, we have these simple cases And if we look at the smaller scales of those cases, we can extract the key physics to predict other complex cases. That is true in many cases, but not always. So if that doesn't hold, that will propagate into the predictions. And that's related into this building block that we know they are deficient to model some physics. They are good for one physics, but not for all of them. And this is a question, it's actually more fundamental than CFD question, is where are these blocks? So how many of these, in a way you can think of this block is like my basis. So I'm constructing this basis and then I project my solution there. So the question is, how many of these do I need? Do I need 1,000, 10,000, million? Do I need only 10? And those 10 will actually give me a very good prediction. So this is mostly based on intuition and the knowledge that we have on the physics, a bit trial and error. But this is the main bottleneck of the model. I mean, in our experience, improving this it really improves the model a lot, or it could be the other way around. So we try to put some thought on this. So this version of the model doesn't account for many things, like roughness patterns. I accounted for some of them, but there are others that they are not there. Reacting flows or multiplex flows, obviously. It doesn't account for mean flow three-dimensionality. That doesn't do very well. And some separation patterns. So we detected that the model is able to capture some type of separation, but separation is not universal. There are many different types of separation, so the model definitely needs to learn more about different types of separations. Another is that it's solver dependent. When I mentioned about the training data, maybe some of you thought that what happens if I change my solver? And actually, it's a bit annoying if you change your solver. The model is trained to be consistent with some particular numerical scheme. If we change the solver, we need to retrain the model. And we didn't find a way of making this universal and independent of the numerical schemes for now. So in a way, we need to go through this retraining process. Then I also mentioned about the confidence score. It's a feature that I really like a lot. It's very nice. But there are also many limitations because the confidence score, if you remember, is asking the question, the model is asking the question, did I see this input data before? But that has nothing to do with the output. So even if the model has seen the input data before, the output could be completely wrong. It's not really bounding the error of the prediction. So we also are trying to improve this. So this could give you some false positives and false negatives sometimes. Then another important bottleneck is not so conceptual or intellectual, is more practical, is to generating the trained database is really very expensive. And we have been training these cases, I would say, for many, many years already. So we keep expanding the database and storage also. The database is petabytes, and we need to then digest that. We need to ask for time in different HPC centers, and they give us a small chunk of time, and we run some cases. And then we have to apply to another place to get time, and we can run. So it's very, because these cases are not very big, we cannot get big allocations. They are many, but very small. So we usually get the small allocations and many of them. And that takes a lot of time and also is very tedious. And the last part is the need of validation data. So at the end, then we need to test the model in cases that we didn't train for. And that will really tell us is the model will learn how to do other more complex cases. And this is very challenging because those real cases are typically experiments. Some of them are numerical, but the real ones are experiments. It's very difficult to measure skin friction in experiments, mean velocity profiles everywhere, even heat flaps. If we go to high speed and roughness, it's even more difficult to find experiments. So this is also a problem. Ideally, we would like to have many validation cases so the model is not biased towards a particular type of cases that we tend to validate against. So we also are trying hard to collect as many cases as possible. So this is the summary of the talk. Essentially here I just summarize the model and the physics we are trying to account for. So what I'm being showing here is this version 1.5 that we have been testing. So now we are developing the version 2.0, and as I mentioned before, so maybe in 1 year, we'll be able to have that version ready. And that version is essentially many of the limitations that I mentioned before, and we learn, and I've been highlighting here, that's exactly what we are trying to correct in this second version. So with that, I hope it was interesting, and I'll be happy to take any questions that you have. Thank you.